in this example, we are given the Fourier transform of some signal xt. And if you look at the Fourier transform, it has a rectangular shape. The Fourier transform is 1 between minus w, and it is 0 otherwise. And we have to find a signal xt whose Fourier transform looks like a rectangle. We have to use the synthesis equation and work it out. So let us write down the synthesis equation first. 1 over 2 pi minus infinity to infinity x j omega e raised to power plus j omega t omega. And then we just replace x j omega in the function. X j omega is 1 only between minus w and w. Therefore, the limits will go from minus w to plus w e j omega t times d omega. And then we integrate it out. E j omega t divided by jt minus w to plus w. Remember, we are integrating with respect to variable omega, not t. So 1 over 2 pi e j wt minus e minus j wt divided by jt. And here we can see that if I bring this 2 inside and take this t outside, then we can get a sign. So ejwt minus e minus jwt divided by 2j into 1 over pi t. And this thing is sine wt. So the signal whose Fourier transform is shown here is sine wt divided by pi t. This signal in time domain has a rectangular shaped Fourier transform. So this signal has a rectangular shaped Fourier transform x j omega that is shown here. Now, if we look at the functional form of xt, we have already seen this functional form when we discussed the Fourier transform of a rectangular pulse in time domain. So if you recall, for a rectangular pulse in time domain, its Fourier transform also had this functional form. And this functional form frequently appears in the analysis of LTI systems and whenever we do Fourier transforms. Therefore, it is worthwhile to spend some time on this function. So generally, function sine pi theta divided by pi theta, because this kind of a function frequently appears. So we give it a specific name and we call it Sinc function. So by definition, Sinc theta is sine pi theta divided by pi theta. So in a way, we are scaling sine pi theta by 1 over pi theta. Okay, and now let us try to understand and see how this function looks like. At theta is equal to 0, we get 0 in the numerator as well as in the denominator. So to find the value of sinc theta at theta is equal to 0, we have to apply L'Hopital rule. If we do that, we will see that sinc theta is 1 at theta is equal to 0. Then other interesting points, in the numerator, we have a sine function, and sine function is 0 at every integer multiple of pi. And in the argument here, we will always get an integer multiple of pi whenever theta itself uh, is a non-zero integer. So whenever theta is a non-zero integer, that is whenever theta is plus minus 1 or plus minus 2, then sinc theta is 0. So sinc theta is 0 at all these values of theta. And if we find the value of sinc minus theta, then we will notice that sinc theta is an even symmetric function. Now in the numerator, sine is an odd function, so we can pull this negative sign out, and we will be left with sinc theta here. So sinc theta, this function has even symmetry. It is an even symmetric function. And now if we plot this function, here we have theta. At theta is equal to 0, the value of this function is 1. At theta is equal to plus 1, plus 2, plus 3, the function is 0. And between 0 and 1, it decreases from 1 and reaches 0 at theta is equal to 1. And because of the evenness, the same thing happens on this side. Between 1 and 2, if we look at the numerator, between 1 and 2, when theta is greater than 1 in the numerator, we have this argument which is greater than pi, and therefore the sign of this function between 1 and 2 is negative. And because of this scaling in the denominator by theta, as the values of theta grows large, the magnitude it decreases. So the magnitude further decreases. And same thing happens on the negative side. Okay. We call this the main lobe of the function, and all these are the side lobes. This is how sinc theta is defined, and this is how sinc theta looks like. Now in our example, we got this function sine wt divided by pi t. Let us try to convert it into a sinc function, and then we will see its plot. So we can convert this into sinc function. First we need a pi here, and then everything else here, that is theta. So to get pi here, there is no pi in the in this argument. So if I multiply pi here, I have to divide pi, and this is my theta. And in the denominator, I also need pi times this value. So I already have a pi here in the denominator, and the remaining terms that I need, I have for theta, I already have t, but w over pi is missing. So I put w over pi times t here, and because I have introduced w over pi in the denominator, so I have to multiply or scale this function by w over pi. and we get W over pi times Sinc Wt over pi. Okay, so this is a scaled and this is a scaled Sinc function. At Wt over pi equal to 0, rather at t is equal to 0. Now, if we are interested in the plot of this function with respect to variable t, at t is equal to 0, Sinc, the argument of Sinc is 0, so this is 1, we will get W over pi. At t is equal to 0, the value of xt is W over pi. And then Sinc function, we already saw that it is 0 at all these integer values of theta. Here, this is our theta. This whole thing is theta. And since we are interested in the plot of xt in variable t, so x of t is 0. X of t is 0 whenever Wt over pi is a non-zero integer value, which means whenever t is m times pi over w. Okay, so this will be, this x of t will be 0 at pi over w minus pi over w, 2 pi over w plus minus 2 pi over w, and so on. And I already have a plot here. The plot of this function, it looks like this. We have just evaluated at t is equal to 0, we get w over pi, and the zero crossings occur at pi over w minus pi over w, and so on. So this is an interesting function, and we frequently encounter it in signals and systems as well as in the analysis, Fourier analysis. Now, if you recall, we got another Sinc function when we discussed the rectangular pulse in time domain. So when we had a rectangular pulse in time domain, we never computed this Fourier transform, but we saw it as a limiting case of a periodic square wave. When the time period of the periodic square wave approached infinity, we were left with this rectangular pulse in the time domain, and the Fourier transform was just the envelope that we were sampling to get the Fourier series coefficients. And the functional form here is again sine theta over theta form. We can easily convert it into a Sinc function using the definition that we have introduced here. But I want to draw your attention to a few interesting things. Here, let me push it aside a little bit. So let me bring it on this side and make it smaller to get some space. For this xt, we were given its Fourier transform, and its Fourier transform made an awful shape. Let me just erase it. The Fourier transform of this function was a rectangular shape, and for a rectangular pulse in time domain, its Fourier transform is a Sinc. So if we have a Sinc function in time domain, its Fourier transform is a rectangle. On the other hand, if we have a rectangle in time domain, its Fourier transform is a Sinc function. So there is an interesting duality between these Fourier transforms. And we will see that this duality holds in general. And that's why whenever we compute the Fourier transform of any signal, we are in fact computing two Fourier transforms. For example, if had we known this property of Fourier transform earlier, we could have guessed that for this shape, we might get a Sinc function as xt. Okay, so that's it. But let us discuss few more important things. Now, if we look at this function and its Fourier transform, and let us try to see the width of this. Let us try to change the width of this rectangular pulse and see how its Fourier transform changes. When we increase the width of this rectangular pulse, we are in fact increasing the value of T1. And as we increase the value of T1, we see an inverse relation here. Here, T1 is in the denominator. So when we increase T1, pi over T1, it becomes small. And the main lobe and also the side lobes, they shrink. So when we expand this pulse and make it wider in time domain, its Fourier transform compresses. And now if we decrease the value of T1 and make it smaller because of the inverse relationship here, the Fourier transform will expand. And in the extreme limit, when we make T1 equal to 0 in such a way that the height of this very small rectangular pulse, it scales with this T1, it scales with 1 over T1 such that the area remains 1, we will get an impulse out of this function. So in the limit when T1 approaches 0 such that the area is kept to 1, we get an impulse in time domain. And when T1 is approaching 0, pi over T1, it becomes infinity, which means that the signal, the Fourier transform, it approaches a constant value. And this is what we saw when we solved or computed the Fourier transform of a unit impulse in time. Now, similarly, here, again, we see an inverse relationship between this capital W and the zero crossings of the Sinc function in the time domain. Now, if we increase the value of W here, if we increase the value of W, pi over W decreases. And in the extreme case, when we make W approach infinity, then here we can already see that I have pi over W here and W over pi here. So this will approach an impulse function. And if we decrease the value of W, if we decrease the value of W and make it approach 0 in the transform domain, in such a way that the area of this rectangle, it remains 1, then we get an impulse function in the frequency domain. And when W is approaching 0, pi over W approaches infinity. And this Sinc function, it approaches a constant value. So if we have an impulse in the frequency domain, then its Fourier transform, if we have an impulse in the frequency domain, then the corresponding signal in the time domain is a constant.